Hello. In this problem, we will look at the real-world applications of redox reactions and how they can be used to determine iron concentrations. The first step of the process is to dissolve the sample in concentrated hydrochloric acid. This means hydrogen and chlorine ions, as well as iron atoms, will be present in the solution. Now we consider possible half reactions. For the oxidation, both iron and chlorine ions are possible reactants, but the voltage of the oxidation of chlorine is very negative, meaning the reaction is unfavorable. For the reduction, chlorine gas is not in solution, so the only possible reduction involves hydrogen ions. Since both half reactions involve a transfer of 2 electrons, all that remains is to sum up the reactants and products and cancel the electrons to yield the overall reaction. The second step of this process is to titrate the iron ions produced in the first step with permanganate. So now we know both the reactants and products of the oxidation and reduction half reactions, so all that's left is to balance the overall redox reaction under acidic conditions. As a note, the process we use here only works under acidic conditions. Okay, so the first step is to balance the oxygens. In the oxidation half reaction, there are no oxygens. In the reduction, there are 4 oxygens in the reactants, so we have to add 4 waters to the products. The second step is to balance hydrogen. Now again, in the oxidation half reaction, there are no hydrogens, and in the reduction, there are 8 in the products, so we have to add 4 hydrogen ions to the reactants. Okay, so now we have to balance charge. In the oxidation reaction, the reactants have a charge of +2, while the products have a charge of +3, meaning we have to add 1 electron to the products. In reduction, the reactants have a charge of +7, the products have a charge of +2, meaning we have to add 5 electrons to the reactants. Now, to balance the overall redox reaction, we need the same number of electrons in both the oxidation and reduction half reactions. To accomplish this, we can multiply both the reactants and products of the oxidation by a factor of 5. So now, adding together the reactants and products of both half reactions and canceling the electrons, we obtain the overall redox reaction. Given the volume and molarity of the permanganate solution used in the earlier titration, we must now find the number of moles of iron ions used. First, we need to convert the 27.64 milliliters into liters, and then multiply by the molarity given. So now we have moles of permanganate, but we need moles of iron ions. To obtain this, we can use the stoichiometry in the reaction we obtained earlier to obtain a conversion factor that will yield the answer. Using the moles of iron ions we calculated in the last step, we now need to find the mass of iron. To do this, we need to first convert from moles of iron ions to moles of iron. To do this, we use the stoichiometry of the reaction we obtained in part A to create a conversion factor between the two. Now, we just need to multiply by the molar mass of iron and cancel units to obtain the answer. Now, because we're assuming the reaction is 100% efficient, the actual and theoretical yields are the same. All that remains is to calculate the percentage of iron of the original sample. To do this, we take the mass of iron found earlier and divide it by the mass of the sample given in the problem, and multiplying by 100%, we say that the final answer is 15.83%. Now, in this problem, we saw one of the practical applications of redox reactions and how they could be used to determine the concentration of iron in the sample. Good luck with the rest of the homework.